Good morning. So, I hope you remember that the last class what we did was on radar, and what was the objective in radar? There were actually Wi-Fi. Okay, so there were Wi-Fi and there were mobile hosts. So there were access points and there were mobile hosts. If you remember, okay, there was access point and there was mobile host. And what did we do? We found out the location of the mobile host. So we had a step of word driving. We did word driving. What was word driving? We initially learned, if you remember, that we initially learned, okay, the spots. We initially learned the spots, and how were the spots learned? It was basically each spot was represented by some signals, a signal vector. Each spot represented by a signal vector. Okay, and accordingly we discovered the location of the spots. Okay, so I guess this is pretty clear to all of you. So now one interesting point which we would make is that in this paper, in this work, what we have done, we have actually assumed what? We have assumed that we know the location of the base station. So what was the assumption? If you think carefully, the assumption was we know the location of the base station. Okay. So assumption is we know the location of the base station. So we know the location of the base station. So see, this work is done on access point, Wi-Fi access point, but this work can actually be extended to cellular tower also. So cellular tower also has the same feature. Cellular tower has also the same feature that it emits signals. Okay, and as soon as it emits signals and mobile phone picks them up, okay. So as soon as it emits the signals and mobile phone picks them up, then it can perform the same task. So in essence, what we can get, so what is about radar? Radar is about indoors localization, and so radar is about indoor localization, but we can also have outdoor localization. Okay, we can also have outdoor localization. So how do we now do outdoor localization? As far as we have studied, how do we now do outdoor localization? We do outdoor localization using GPS. If you remember, we do outdoor localization using GPS. What are the problems of GPS? The problem of GPS is it is power hungry. Okay, this is a huge problem of GPS. It is power hungry. But see, the cellular tower signal we are always receiving. So we are always receiving cellular tower signal. Okay. So if we can use them and do triangulation and can find out the location, then that would be the most cost effective means energy effective method. So what is the idea? That use cellular towers signal information, use cellular tower signal information, use cellular tower signal information and use cellular tower signal information and accordingly use cellular tower signal information and accordingly build up the location information. So what would happen then? This can basically replace energy hungry GPS system. But what is the problem? So there are many problems with this thesis. So what is the problem, or rather what are the problems? Okay, what are the problems? So there are many problems. One problem which we will tackle in this is that actually if you see, if you think how cellular towers is put, that somebody's roof is available, uh, the company put a cellular tower. So cellular tower is put completely haphazardly. So cellular towers put haphazardly, and there is no information about the location of the cellular towers, of the exact location of the cellular towers. Okay, so there is no database as such that from which points there the cellular tower is there. So there is no information about the exact location of the cellular tower. Okay, so this is a problem. So this paper is actually will try to actually locate the cellular towers. So previous paper we were using base stations to locate individuals. Now we will use individuals to locate cell tower. So understand this. So we will use individuals to locate cell tower. Okay. So previous one, base station, use base station to locate individual. Okay. So this is a paper which is doing the opposite work. So how to do this? Okay. So how to do this? So again we will have to have the same word driving phase. So we have to have the same word driving phase. But who will word drive? Previously what was happening? Individuals were word driving. But here you cannot word drive the cell towers. The cell towers are actually there. So what you have to do, and remember cell towers, so previous case how much was the area? The area was, if you remember, it was 43 meters by 20 something meters. Okay, so it was a small area. But as soon as we talk about cell tower localization, it is like area would span an entire city or at least a locality. Okay, or at least a locality. So it's a big area. And what has to be word driven? So word driven is person moving and collecting signals from cell tower. Okay. So, person moving and collecting signals from, but person moving, how would person move? Will he walk? So, walking kilometers would be very difficult. So, what has to be done? That person perhaps will move in car. Okay. So, what is what driving now? So, what driving is a person or persons, okay, persons moving in car, okay, and collecting information So, this paper is on that. So, the paper is came out in 2010 in Ubicom. Okay. So, what is what driving? What type of what driving they have done? Let us see. So, the data description says that they had a what driving trace covering 3 areas in Greater Los Angeles area. Okay. So, they had 3 areas in Los Angeles. And what are the 3 areas? They were actually considering the downtown, the residential area, and they were considering the rural area. So, these are the 3 areas where they were covering, and if you see, downtown is 3.5 kilometers into 4.2 kilometers, huge area. The residential area is still much bigger, 6.3 kilometers into 17 kilometers, while the rural area is in the Victor Valley of San Bernardino County. Okay, that is actually 35.4 kilometers into 36 kilometers. So, they were driving through the roads of this rural areas, the residential areas, residential areas, and they were driving through this rural areas, residential areas, as well as through the downtown. Okay, fine. So, and what were they doing? Basically, they were doing this for 2 months. They did this for 2 months continuously. Think about the research they are doing. For research, they are actually driving for 2 months, February and March 2009. Okay. So, they were driving continuously for 2 months, and what was happening? The GSM signal strength measurement and their locations were recorded every 2 seconds. So, every 2 seconds the GSM strength and their location was located, and the speed of the car averaged 32 kilometers per hour. Okay. So, this way they were collecting a huge amount of data. So, see how much amount of data they have. They have 2.6 million signal strength readings from 105 means 105,000 or 1,05,000 unique locations, resulting in 24.8 RSS reading from different cell per location. So, per location they were getting 24.8 RSS readings for different cells. Now, each cell tower. So, this also we should remember that if you think this is a area, the car is moving, okay, and a cell tower is there. So a cell tower typically will have multiple cells. Okay. When you have cell tower, you will put one cell in east, one cell in north, one cell in west, and one cell in south. This way you will put various multiple cells, so that the cost of the cell tower installation is maximally recovered. Okay. So what we see, that each cell tower has 2, 3 or 6 cells attached to it. Okay. Each cell tower has 2, 3 or 6 cells attached to it. Fine. And we know which cell belongs to which cell tower and the actual location of each cell tower. So this is known, means we know, means this is known, so that people can calculate how much mistake we are doing. Okay. So they already know so there are already knows the location of the cell tower and calculates the location using their algorithm. Okay. And then A minus B shows the error in the system. Okay. Fine. A minus B shows the error in the system. Very good. So this is about what driving. So now how to do it? So now how to do it? There can be various methods. One is, say I am going through a road and the cell tower is here. Now I am getting signals. I am taking signals at every 2 seconds. So I am taking signals. So SS1, SS2, SS3, okay, SS4, SS5, SS6, 7, 8, 9. See, I have got 9, out of which SS5 is the strongest signal. Okay. Fine. SS5 is the strongest signal. So then what you do, SS5 has given XY. Okay. SS5 has given XY. So what you do is that you tell SS5 is at XY. So you tell the cell tower is at XY. If you remember previous case also we did this. So this is what is called strongest signal. Okay, strongest RSS. Okay, so you get SS5 as your point. The other way is to do that. Okay, SS. So what we have got here, we have got X9, Y9, X8. So this is X5, Y5. Let us think. X8, Y8, X7, Y7. Okay. So this way we have. So now what we can do, we can think the location X, okay, X cell tower is equal to summation of Xi and SSI. Okay, summation of Xi SSI by summation of SSI. So what is happening? You are basically doing a weighted summation. Okay, you are doing a summation of weighted summation. So what is this understanding behind it? So for Yi I write Yi SSI summation of SSI. So what is the reason behind this writing? So the reason behind this is simple, that we think, again last class also we told that signal is roughly corresponding to distance. Okay, signal and distance are roughly corresponding. So if you have stronger signal, that means you are, so if you have a stronger signal, that means you have your position, the position where you are, the cell tower is close to your position. So you should get more weight. Okay. So when it is calculated, since you have stronger signal, your position should get more weight. So what is happening? If x is 5, so if the fifth position which has x 5, which has x5, y5 and has a signal strength ss5, okay, this is position 5. So what is happening? I am multiplying x5 with ss5 because ss5 is very high. So in this summation, what is happening? The summation is getting biased toward x5. So what will happen in the end? You will get the cell tower which is close to x5. Okay. So this is called weighted average. Weighted average. Okay. So this is simply a centroid. I am just taking a centroid. I am just finding a centroid. If you think I am just finding a centroid using weighted average. Okay. So now let's see how things work. So see this picture now. The picture, there are two pictures. One is the strongest RSS written, another is weighted centroid. So what is strongest RSS? What is x-axis? X-axis is error in kilometers and y-axis is again the probability of that error. Okay. So now again we come to this reading of this graph. So there are three places. The black is for rural. Okay. The red is for residential and the blue is for downtown. Fine. So now what we see, take rural case, the strongest RSS works best. For rural case, the strongest RSS works best. How are we understanding? What we are understanding, see, this is the picture which shows that for around 70% of the cases, the error is less than even a kilometer. So what is happening? If I see strongest RSS with respect to rural, if we see strongest RSS with respect to rural, what is the picture we are getting? What is the picture we are getting? We are getting that the error less than a kilometer, less than 1 kilometer is at about 70% of the cases. But in downtown, the error is higher, and in residential area the error is even higher. So if I think of 70% cases, if I think of 70% of cases in downtown, then it will be around 6 kilometers, and in residential areas it will be around 10 kilometers. So but if you see the weighted centroid, what is happening in the rural? The weighted centroid is becoming very bad, while in downtown the weighted centroid works better, but still strongest RSS works better. Okay. So see in if you see in downtown, what is happening? See rural, if I think 70% of the error, then 70% of the error is more than 10 kilometers, whereas here 70% of the error was just 1 kilometer, not 70%, but like 67% of this was just 1 kilometer. Here 70% of the error is around 10 kilometers. So it has deteriorated so bad. So what is the reason? Because intuitively, if we think, strongest RSS is taking just one signal. So we have seen that what is strongest RSS? Strongest RSS is just concentrating on the strongest signal and blindly putting XY as that of the strongest. Okay, while is blindly putting that of the strongest signal. While in weighted centroid, we are actually doing a much more sophisticated job. But even if we have done a sophisticated job, weighted centroid is not performing as good as strongest RSS. So why is this happening, and especially in rural situation? So see, what is happening is, if we think that in rural situation, the basic point is the cell towers, because there are very less house etc., very less houses etc. So the cell towers are near the street, okay, or near the highway or road, whatever you tell, okay, near the highway or road. Okay. So what is happening? As soon as you are giving strongest RSS, that means you are giving the location of the road, and the cell tower is just beside the road. So immediately you get very good cell tower localization. While in downtown or residential area, this is not so. Okay, in downtown and residential area, this is not so. So that's why it doesn't perform so well in downtown and residential area. So some people are not getting video, it seems. Okay, yeah. So fine. I guess this is clear. So next point is simple. Next point is simple, that okay, we understand that RSS is good, strongest RSS is good in rural area than downtown and residential area. This is fine, but why strongest RSS should be better than weighted centroid? Because weighted centroid is a much more sophisticated method. We are doing a much more sophistication. We are doing much more sophistication to get the information. So what is essentially happening? If we go back to this picture again, let me draw that SS5, SS6, SS7, SS8, okay, SS4, and this way it goes SS1. So if I have this 8 information, so as the signal is fading, the distance. So what is the assumption in this weighted centroid? The assumption in this weighted centroid is simple. The assumption is signal strength is basically proportional to, or can be used as a proxy to, distance. But as signal become low, as signal strength becomes low, it doesn't correspond to distance. So that's why when you are trying to do this weighted average, it essentially breaks down. Okay, when we try to do the weighted average, it essentially gives wrong information. When we try to do the weighted centroid, it gives wrong information. So I guess it's clear, because see, SS1 may be 50, SS2 may be 60, SS3 may be 70. I'm just writing in the, it should be actually minus, but let me write it in the positive way. So it is 65, it is 55, it is 40. So this 40, so if I just plot 40 is to distance, okay, and distance 55, 65. So let me just think that this is distance and this is signal. So this, if this follows something like this, we are done. But if this begins to follow something like this, where at one point it becomes completely unpredictable, then weighted average doesn't work, weighted centroid doesn't work. Fine. So then let us see things in a bit more way. So this is the table I have been talking about this. So in downtown we see that strongest RSS and weighted centroid works a bit well, because in downtown you are actually moving a little better, but in residential area and rural area it is actually not working. Okay. So now we can dig a bit deeper. Okay, we can dig a bit deeper and see that what bad signals and what good signals we are actually collecting. So see, the same picture which I was trying to draw, see they have drawn a scatter plot. What is x-axis? X-axis is the error of the strongest RSS. Okay, error of the strongest RSS. Error of the strongest RSS. So if whatever the RSS, so y-axis is the RSS and x-axis is the error. So RSS, the best RSS maybe is minus 10 dB. Okay, this is the best RSS. Then minus 20 dBm. Okay, so this is slowly coming down. So they say minus 60 dBm. Then it becomes very bad, minus 70 dBm. That is actually very bad. Okay, minus 70 dBm. So that is very bad, and minus 100 dBm means the signal is actually very weak. Okay, so now see, y-axis is the error. So I see a signal. Okay, I see a what are they doing? Basically, they are at distance x from the cell tower, and they see a signal which is say 110 dBm. Okay, so now they are plotting this distance. Okay, they are now plotting this distance. Okay, now you see if it corresponds exactly. So this 110 dBm corresponds to an exactly 1x. Then what would happen? Then the simple thing which would happen is that you would get one single line. But what is essentially happening here? You see there, here you are getting one line, then it is getting very scattered. Okay, so here you are getting one line, but then it is getting very scattered. What does that mean? That even if I have say 110 dBm, I can have error of 5 meter and I can have error of 25 meters. So it is, this x can be anything, it can be anything from 5 kilometers to 25 kilometers. So that means it cannot be actually used as a proxy to distance. Fine. So then what they do is that, okay, so don't consider. So then the point is very simple. Don't consider all the signals. Consider only strong signals. So what have we learned? Don't consider all signals. Okay. Consider only stronger signals. Okay. So what have we learned? Don't consider all signals, consider only stronger signals. And what does the stronger signals means? What does the stronger signals mean? Basically, that means you consider signals which are greater than 60 dB. So that means you consider signals which are greater than minus 60 dB. So now see, the next picture is cutting from here this part, and actually creating a new picture. And here you see that around 60 dB the things becomes bad, but beyond that more or less it is consistent. Beyond that it is more or less it is consistent, that if you have a signal strength of minus 55 dB, then your error is almost same. Okay. If you have minus 55 dB, then your kilometer would be roughly corresponding to say 0 to 1 kilometers. So you see the previous one x axis was from 0 to 40, this x axis is from 0 to 8. Okay. So the entire error, so only if we consider this 1, 2 stray errors, the entire error comes around 1 kilometer. The entire error comes around 1 to 2 kilometers. Okay. So what is the learning from here? The learning from here is that if you have to consider signal as a proxy to distance, only consider those signals which have higher decibel within it. So and here the typical is that you only consider minus 60 and above. Okay, very good. So once you have learned this, so this is now I show you a picture. So what is happening is that we are what driving point. So this is a bounding technique. So we are considering a bounded area, and this bounded area may be downtown. Okay, and the car is moving, and you see there are inside roads also. It's not that only there is road at the perimeter. So there is road at the perimeter and also roads inside as it should be. Okay, roads at the perimeter and roads inside. So see, I will just see this, show you this picture and go back and ask one more time that why RSS would weighted centroid would work better in downtown rather than in the other areas. Why should weighted centroid work better in downtown? Because what happens, you see, a downtown has various small alleys and various roads around it. So if a cell tower is in the middle, then you will get many strong signals. So this would work good. This weighted centroid would work good. The weighted centroid would work good if one gets many strong signals. And what happens, since a downtown has various small roads, the road content is much more in downtown than in other areas. Okay. So what is happening, if the cell tower is in the middle, the car is moving in all these 4 directions and getting many stronger signals. While in a rural area, the road is very sparse. So there will be road like this and the cell tower is besides this. So only once or twice the car is getting strong signals. All the other signals are becoming weak. So as soon as you have many strong signal, weighted centroid can work, but as soon as you have weaker signals, weighted centroid fails miserably. Okay. So now coming back to this, so you have bounded techniques and you get cell tower C1, C2, say you have cell tower C1, C2 somewhere here perhaps, we don't know where it is, but you have what you take is A's coordinate is 515 and it is getting cells, so 2 cells C1, C2 RSS as minus 65, minus 50. For B it is getting, B is at 810, XY is the coordinate and 2 signals it is getting minus 70, minus 60. C is 72 and it is getting minus 80, minus 90, minus 80. So this way it begins to get all sorts of information. Okay, so this is how information is collected. So now let us think, what are the steps we can do using this bounding technique. So we have a bounding technique. What are the steps which we can do? So one problem which they identified, is, see, if I have a bounded area, so there are cell towers outside the bounded area and there are cell towers inside the bounded area. Okay, so cell towers outside the bounded area and cell towers inside the bounded area. So what is happening? The error is more if it is outside the bounded area. So but we don't really want to find cell towers positions of outside the bounded area. We only want cell towers inside the bounded area. So how to identify which cell tower is inside and which cell tower is outside? So now the next question which is important, that how to identify which cell tower is outside and which is inside. This is a question which needs to be tackled. Okay, how to identify which cell tower is outside and which cell tower is inside. So one is, see, the one intuition can be very well. So one is RSS thresholding. First of all, what we do, that we remove, so we remove information, we remove all those cell towers from whom the RSS received is less than 60 minus 60 dBm. Okay, so RSS received is less than minus 60, which is a threshold. Okay, so here we are writing a threshold concept. So the threshold is minus 60 dBm. So what is happening? Simple, that you remove all those cell towers from whom, or all those cells, rather let us write cells, not cell tower, because a cell tower consists of a lot of cells. All those cells from whom the RSS received is minus 60 dBm. Okay. The second point is, say you boundary filtering. So what is happening? The understanding is this, that the understanding is clear, that if a cell tower, so this would actually remove many cell towers here, but it would not remove cell tower which is just near the boundary. So this RSS thresholding doesn't remove threshold cell towers which is just near the thresholding, and it can perhaps take out some of the cell towers, some of the cells which are inside. Why? How can it take out some of the cells inside? Because some of the cells maybe, it may have covers, it may have walls, or it may be high up in the building, and you are driving the car down, so it may be higher up, maybe 5 stories, 10 stories higher up. So you can have a lot of obstructions, and which may ultimately result in some of these cells not being identified. Okay, and this cell may be pointing south, and you have been continuously moving north. Okay. So the signal, although the cell is inside the bounded box, the signal received may be less than minus 60 dB. So what they found, that just doing this, they eliminate 20% of inside cells and leave 12% of outside cells. Okay, so they still leave 12% of outside. So blindly thresholding would not work. The second is called boundary filtering. So what is boundary filtering? The second is boundary filtering. So boundary filtering means a simple thing. So in boundary filtering, what we will do? The intuition is, again, think carefully. What is happening? This is a cell tower, this is a cell tower. Okay. So now the intuition is, although this cell tower has greater than 60 dBm, minus 60 dBm signal, the strongest signal received about this cell, cell maybe says this cell is CL1, the strongest signal received is greater than minus 60 dBm at this point. But this point is in the perimeter. So now the heuristic says, if the strongest signal received from a cell, if the strongest signal received of the cell, say, is equal to S, if the location where S is realized, there, if the location where S is realized lies in the perimeter, then what we say, if a strongest signal realized lies in the perimeter, then we say that S is, then we say the tower is, or the cell is outside the bounded box, bounded area. Okay. So idea is simple. If it is inside, then there may be stronger signal here, but when I am going through a inside road, then I will get another very strong signal. But if it is outside, only I will get strong signals in the perimeter. But this, although is a nice observation, this also is a nice observation, but still there are problems, because you see, again, there may be a road like this. So there may be the perimeter road and there may be a parallel road very near to the perimeter, and this is, I am ward driving and I am collecting signal here. So I have collected signal here and I have collected signal here, and there is no guarantee that this, if this is SS, say this is a point A and this is a point B, so SSB and SSA. So there is no guarantee that SSA would be greater than SSB, because DA is roughly same as DB. DA is a little greater than DB, little less than DB, but SSA may not be greater than SB because of various environmental situation. When he is moving from this point, there was some wind, so the signal has gone down. So that is exactly what we have seen here. See again the picture, again the this so at 1 kilometer, at 1 kilometer, 1 kilometer you can get minus 60 dB, also you can get minus 55 dB, whereas maybe you are at 2 kilometers, then you get maybe 58 dB, minus 58 dB. So, what is happening at 1 kilometer, you are getting minus 60 dB, while at 2 kilometers you are getting minus 58 dB. Okay. So, these are situations which can happen, and if 1 kilometer is the perimeter, while 2 kilometers is the road inside the perimeter, then your heuristics that the strongest signal of the cell towers which are outside would reside in would be found only when we are traveling the perimeter, that may not hold always. Okay. So, this is a problem. So, boundary filters may not work always, but anyway, boundary filter is a good idea and it solves. So, we are actually 12%, we are taking falsely 12%. So, that 12% may get down a bit. Okay. The next thing which can be done is taking this concept about tower based regrouping. Okay. So, taking this concept of tower based regrouping. So, what is a tower based regrouping doing? So, in tower based regrouping, what would happen? So, as I have told that you are getting each tower may have 2, 3 or 6 cells. Okay. So, now in your database, through all these 2 techniques, boundary filter and etc., what we are getting? We are getting, and from the cell information, you can actually decipher in which tower it belongs. The cell actually sends out information declaring which tower it belongs. So, that basically means all the cells coming from the same tower has some bits in their signal as common, has some bits in their signal as common. Okay, has some bits in their signal as common. So, what essentially happens? It has some bits in their signal as common. So, what essentially happens? Essentially happens is that I can understand that out of the 6 cells, how many have I captured? How many are in my database? So, what is happening is I have a bounding box. I am doing a RSS thresholding. Okay, and I am doing a boundary thresholding. Okay, and then I am actually creating a database of cells inside the boundary box. Okay. In this database, still there may be some cells which are wrongly classified. Okay, which are wrongly classified. What does that mean? Which are wrongly classified? That means that cell is actually outside, but the database has put it inside. Okay, the cell is actually outside, but the database has put it inside. Okay, so this is the situation. Now think, see, so this is a cell tower outside. It has this. What would happen? Which cell would come inside? Only the cell which is facing the road will come inside. All the other cells which are not facing the road would not come inside. Whereas if you think a tower inside, all the cells, whichever direction they are facing the perimeter or some road inside the boundary box, which are actually facing some road inside the boundary box. Okay, that's why one thing would happen, most of the cells inside, most of the cells of a cell tower would not appear in the database if the cell tower is outside. If the cell tower is outside. So what is happening? Very simple, that this would make some mistakes here and there, that is fine, this would make some mistakes here and there. One cell, a cell tower is there and which has 6 cells, out of which maybe 4 will come inside. Okay, this has a cell tower out of which 4 may come inside. Okay. However, it would not happen that all of them would actually come inside. Okay, all of them would actually come inside. All of them, all of them would actually come inside. Fine, this is clear. Anybody has any questions about it? Okay, very good, very good. Okay, so now where are we doing? So now with all these 3 techniques, so let me again write down the 3, it's written there, but let me write down the 3 things. RSS thresholding, boundary filtering, and then tower based regrouping. All these 3 actually is bringing in only cell towers which are inside. So now we deal with cell towers which are actually inside. Okay. So now upon this, if we actually do weighted both strongest RSS and weighted, see the x-axis, x-axis is the error in kilometer and the y-axis shows the CDF. Again the CDF means what? Take this third picture, maybe the weighted RSS 4 kilometers or less error is 30%. 4 kilometers or less error is 30%, while for strongest RSS 4 kilometers or less error is like 95%. So still strongest RSS, so with all this calculation, all this thresholding etc., still strongest RSS is performing better in almost all of the cases. Residential area it performs better. In downtown the results becomes comparable, but still strongest RSS performs better. So what is essentially happening? Essentially what is happening? Still all these calculations you are solving the problem a bit, but still not good enough to actually come as close as strongest RSS. And what we know about strongest RSS? Strongest RSS is inherently faulty, because strongest RSS is showing you just the person who is standing on the road and the cell tower is away from the cell tower. You don't have a cell tower standing in the road. Okay, you don't have a cell tower standing in the road. The cell tower would be somewhere beside the road. It may be 500 meters away from the road, or yeah, sometimes 300 meters away from the road, but it will never be on the road, and that kilometers it cannot actually solve. Okay. So then what? So see, now see this result. The previous result, if you remember, was 2.75, 7.5, 0.7. Okay. Now it has become C2. It has become 267. 267, 139 meters. So it has come down in meters. Okay. Previously it was coming at kilometers. Okay. It was coming at kilometers. Now it is coming in meters. Okay. So you can understand your 7.5 kilometers means is ridiculous. 7.5 kilometers means it is almost ridiculous that somebody is telling I am in Delhi railway station and the result is showing that he is at Delhi airport, something like this. Okay. So it is ridiculous, but now see in the weighted bounding what happened, it was 2.83, that has become 785, not improved as good as that. 8 kilometers, that has become 1.3 kilometers, and 7 kilometers have become 5.5 kilometers. So still weighted centroid is much worse than strongest RSS. So this is not according to intuition, because weighted centroid we are doing better work. Why is it not coming down? So the next thing is important. The next thing is what we now realize. So if we think carefully, what we realize is that this information is there, that there are cells. So this is what localization of cells and not cell towers. Okay. So what is this result bringing out? What is this result essentially bringing out? That say there is a tower, there is some cells here. Okay, there are 3 cells. So there is a tower, and 3 cells, and this localization is putting cell 1 here, cell 2 here, and cell 3 here, whereas all of them are in the same tower. Okay. So this is a interesting thing, that for the same cell, so for the cells which reside in the same tower, for the cells which resides in the same tower are actually not localized in the same point, they are localized in different points. Okay. So now can we leverage this and build upon it? Okay. So now we do the cell tower optimization. So now what is this cell tower optimization? Now we say simply that, okay, from these cells we have got some RSS which are greater than 60, minus 60. From this cell we have got some RSS which are greater than minus 60. From this cell we have got something which are greater than minus 60. But these are all coming from the same location. So these are all coming from the same location. Think carefully, these are all coming from the same location. So previously what are we doing? Taking all these signals SS1, SS2, SSK, okay, we are doing a weighted average of SSI into XI, summation of SSI and SSI into YI, summation of Y SSI. So this is what we are doing and trying to find out for this. For this again we are doing SSJ, and for this we are actually doing a SSP, something like the summation of SSP or SSI. So we are actually doing 3 different three different weights and calculating three different ones. So why do this? Combine. So now since they are in the same cell tower, they are in the same cell location. So combine all the signals which are greater than some threshold, combine all the signals which are greater than some threshold and then take the weighted. Okay. So this is what you see, that if I have one cell, then if I have one cell, then these are the green part is the signals which are greater than the threshold. While if I combine all the cells, you have a much better and it is a much symmetric information, because here you see this case, this was the cell tower which was discovered and all the signals are actually to the right of that. Okay, all the signals which were discovered are to the right of. This is the cell tower which is discovered, and the signals which were used are, none of the signals are to the to the right of it, all the signals are to the left of it. All the positive signals or the green signals are to the left of it. There is none which is right of it. But now when you have combined the cell towers, then what we are getting? We are getting the signals which are equally spaced, okay, which is symmetric and evenly spaced. So now what we are getting is basically getting an evenly spaced cell. Okay, we are getting an evenly spaced cell, and this would actually give much better localization. So now after doing this, what are we getting? See this. So before cell combining, so x-axis is top k RSS. Okay, I take the top k RSS, okay, and try to work on weighted centroid and try to work on strongest RSS. So if I take the top k RSS, what is top k RSS means? I am basically taking the top k signals. Okay. So top k signals, beyond that I am thinking all the signals are deteriorated a lot, so don't take it. So as see this x-axis, so top k I first taken 5, then 10, 10, 15, etc. So as soon as I begin to take more and more, I increase the value of k. So top 300 RSS means top 300 most strong or strongest signals which I have got. So top 300 strongest signal, the last one will be very weak. Okay, so then that would actually give you a lot of error. So what is happening, as k increases, weighted centroid actually begins to work much worse. So if we begin to increase k, weighted centroid works much better. Now, but if you go to this case after cell combining, so what is happening? As soon as you are increasing k, because what you are getting much better quality RSS. You are getting much better quality abundant RSS. So it is happening that slowly, if you go on increasing k, at certain point of k, around 50, 60, around 60, the result becomes best. So what is happening around 60? So around 60, if you see, so around 60, the result becomes best. So what is happening? So around 60, you are getting the best RSS. Now even if you increase more than 60, the RSS begins to deteriorate. So if you take the top 60 from those signals, so if I go back here, if you take top 60 from this zone and work, then you are getting the best localization. So you are getting the best localization. So what has happened? So previously we couldn't beat strongest RSS. We couldn't beat strongest RSS. And why couldn't we beat strongest RSS? Because of one simple reason. Because of one simple reason. What is that simple reason? The simple reason is we were not getting enough strong RSS. So as soon as we were going for weighted RSS, we were using poor signals, and those signals were actually creating problem and the error was creeping in. Okay, after cells have been combined, the result is becoming best. Okay, after cells have been combined, the result is becoming best. After cells have been combined, the result is becoming best. So if we use the 50 combined things, then you get very good RSS and the localization becomes very good. So now you see, okay. So what we have seen that see this case. So previously it was 267 and it was 785. Okay. So after combining means after combining the cells, this is becoming 163, while weighted centroid is becoming 152. Okay, weighted centroid is becoming 152 in downtown. So in downtown, let us write in downtown what is happening. It is 163 to 152. Okay. So in residential area, it is 91 to 55. And in rural area, it is becoming 229 to 167. So see, interestingly, where did we start at rural? What was the initial figures of rural? Do you remember what are the initial figures of rural, downtown and residential? So this is downtown, this is residential, this is rural. Okay. What were the initial figures? The first figures. So let us go back and see what are the first figures. So if we go back, okay, I think I missed the this is what, okay. The first is, this is 0.7, this is 7.5 and this is 2.75. Okay. So what is happening? This is very interesting. See, the initially rural was best, but it couldn't improve 0.7 to it improved to 167. The best we are getting 167 meters because it is not so sparse. It's not so dense. The cell towers are not so dense also. For residential area, it was 7.5 kilometers. It is improving hugely and becoming just 55 meters. We started with 7.5 kilometers and we have reached 55 meters. Okay. And here we started with 2.75 kilometers and we have reached 152 meters. Okay. So this is how you do cell tower optimization. Okay. So I guess we finish the cell tower optimization in this now. Okay. So once we are done with cell tower optimization, we will actually talk about something different, or the last of our talks, in about pin lock, okay, which is a precise indoor based localization. So can you tell me how to, we have to put up a new slide, how to do it? Okay, so I am back and now we talk about our last slide and last concept of precise indoor localization. So still now what we have done, again if we just recollect, we have done the GPS, which is a precise outdoor localization. We have done GPS, which is precise outdoor localization. Then we did radar. So radar is an indoor localization, but what was the error? The error was like 3 meters, 2 meters, okay, 2-3 meters. So what would happen if we have 2-3 meters? Like take a example, simple example, that you are actually, so this paper's name, it's interesting. This paper name is "You Are Facing the Mona Lisa." So this paper's name is "You Are Facing the Mona Lisa." Okay, spot localization, spot localization using physical layer information. Okay, so you are facing Mona Lisa. What localization? So see, if you are facing Mona Lisa and it is giving a error of 3 meters, then what would happen? It would actually give you information about. So what is the point? You are facing Mona Lisa and you have a mobile phone where the information about history of Mona Lisa is coming. Okay, and now mobile phone have to understand precisely, mobile phone have to understand precisely that you are actually facing Mona Lisa. Okay? The mobile phone have to understand precisely that you are actually facing Mona Lisa. But this may be difficult because if it is 3 meters, instead of Mona Lisa, it may give some other pictures which are just beside Mona Lisa. Okay? So then the requirement is spot localization, exact micro localization can we do using mobile phone. So this is a paper which talks, and this from Mobicus 12. Okay. So how are we doing still now? Still now what are we using? We are using RSS. Okay. We are actually using RSS. Okay. Now they are telling don't use RSS. So they are actually proposing something very different. So they are telling that model digital signal radios use OFDM communication. Okay. Model digital signal radios use OFDM communications and transmit signals across orthogonal subcarriers at different frequencies. Okay. So it has different frequencies. Maybe there are 48 orthogonal subcarriers. If you see, there are 48 orthogonal subcarriers and it is transmitting at different frequencies. Each transmitted symbol uh, is modulated, each transmitted symbol is modulated on a different subcarrier F, and you have 48 frequency subcarriers. So so these are called actually channel frequency response. Okay, these are called actually channel frequency response. Fine. So can we use this to target the problem of spot localization where success is defined? So success is defined as the ability to place a device within a 1x1 meter area. So now you have to have a 1x meter area of success. Okay, fine. So this is what you have to achieve. So now if we have to use this, okay, if we have to use this, carefully think, if we have to use this, two important properties of the CFR are of interest. Okay. There are two important properties of CFR. So, two important properties of CFR are of interest. One is the CFR changes entirely. Okay, the CFR is a signal which changes entirely once a transmitter or receiver moves than a fraction of a wavelength. So, CFR changes entirely once the transmitter or the receiver moves a fraction of a wavelength. So, a wavelength will be typically say 12 centimeters. Okay. So, what is happening? So, see, the intuition is that if I move 12 centimeters, so I am breaking the entire floor into small grids of say 2 centimeter into 2 centimeter or 12 centimeter into 12 centimeter, and if I see the channel frequency response here, the channel frequency response just the next would be actually different. So, what is happening? See, in RSS, if you move 2 centimeters, the RSS doesn't change. It can change, but it would not change appreciably to actually use it algorithm. While the CFR may change appreciatively to use it algorithm. But what is the problem? What would be the problem? Can you tell that what would be the problem? The problem is if something changes so frequently, then something it may not be stable. So, what can happen? It will change also if you are standing at the same position. So, the second point is thing, even when the device is static at a specific location, even when the device is static at a specific location, okay, even when the device is static at a specific location, then what happens? Even when the device is static at a specific location, then what happens? Okay, even when the device is static at a specific location, the CFR experiences channel fading. So since we are using these channels, the CFR experiences channel fading. Okay, the CFR can experience channel fading, and then the signal at the same location can become different. So, if the signal at the same location becomes different, then even if it is different at different location, we cannot use this. So, only time we can use is when can we use a signal? When can we use a signal to denote a location? A, when it is different in different locations, or and it is same in same location. Okay. Now, this doesn't hold. If this doesn't hold, then it will not hold. So, now what they say that fine, it is sure that this changes a bit. So, if you are standing in the same position also, it changes a bit, but does it change very randomly? Does it change very randomly? So, then what they do, see this picture now. This picture is showing the amplitude and phase of the subcarriers at the same location. The data is collected many times at the same location, and you see that all of them are not same. All of them are not same. So, if they are same, what would have happened? They would have come in a single line, but you see that they are roughly following the same things. So, they form clusters. So, what happens is that this change due to channel fading is there but it doesn't mean that the change is completely random. So the change is not random. So if we do a little bit of machine learning, or if we do a little bit of uh, mining, we will see that these things, this channel response at different times actually can be clustered around maybe one or two clusters. Okay. So what is happening? See, if you see this picture, that they have got two clusters along which the channel response has been clustered. Okay. So all the channel responses can be actually clustered around two clusters, and as if you take the cluster head and work on this should actually solve the problem. So then this is, it is not same at same location, but it is actually forming clusters. And then see, clusters can be formed, but how many clusters? If I form 50 clusters, then those clusters doesn't have any meaning. So now I have to see that how many clusters normally they form. So if I go to this picture, I see that number of unique CFR per location, we see that most of them, again the CDF, 50% of them, okay, around 50% of them forms one cluster. Then around 80% of them, 70% of them form two clusters. Then 4 clusters is like, within 4 clusters there is 85%, but there are some as high as 19 clusters. So 19 clusters is bad news. Okay. So if I have 19 clusters, that means that is bad news. Okay. Because you can have 1 cluster, 2 clusters, 4 clusters, but 19 cluster is very, very bad news. That means it is not same in the same location. So what is happening? First we say that, again, just for your for to pick up get the basic philosophy. Basic philosophy is, when can a signal be used to denote a location? There are 2 points. When it is different in different locations. So if the signal strength is same in different locations, then you are confused. Okay. This is one, and more importantly, it is same in the same location, because it has to be same in the same location at all time. So in the morning if it is 5 and in the evening it is 7, then that is very problematic. But what we see, that since this is a physical level information we are calculating, it is actually not very robust. There is channel fading, and due to environmental conditions etc., there will be channel fading. So those channel fading actually makes the signal different. But is it very different? So that's why what they do, they try to cluster all the signals received, and when they cluster all the signal received, they basically get, say, 2 clusters. But there are some cases where they get as high as 19 clusters. So if I say that these signals which I am getting can be clustered into 19 clusters, that is as good as saying all the signals which I am receiving at the same location is different. 19 clusters is no good thing. We can have 2 clusters, 3 clusters, 4 clusters, etc. So next question which can be asked very clearly, okay, we are getting 19 clusters, but all the clusters are equal, or are all the clusters equally dense? So what is the meaning of equally dense? So are all the clusters equally dense? So this is what we can ask, are all the clusters equally dense? That means what? We have points, data points, say we have 1000 data points. Okay. So 1000 data points, and it is forming 20 clusters. 20 clusters. So equal data points means each cluster would have 5% of data. However, if this happens that the first cluster has 50%, the second cluster has 30%, the third cluster has 10%, and the fourth cluster has 5%, while the next 16 clusters have 5% together. That means most of the data points are falling within this 5 clusters for the first 4 clusters, which would mean that this is very good news, that even if I have 19 clusters, if most of my data falls in the first 4 clusters, then at least I am saved. So this is what you see. Now the most frequent cluster is like 60%, 67%, then it is coming 7, but 6 is just inside. Okay, 6 is just inside this, then 14%, then 9% and 4%, and all others makes just 6%. So although we are seeing 19 clusters, we have just 4 clusters. All the other clusters can be ignored. Okay. So with this understanding that although it is not in the same point, but it forms 4 clusters at most, not more than that. Then we are done and we form the architecture. And what is the architecture? So the architecture is this simple thing, this architecture where we see that we have the CFRs, from CFRs we get the clusters, okay, we get the clusters and we make the clustered database. So we make the clustered database. So how do we make this clustered database? This is again I hope you are understanding that all this localization would have some sort of word driving. Okay, I hope all of you are understanding that all this localization would have word driving. So in this word driving phase, what are we getting? In this word driving phase, what are we getting? We are getting basically clusters. Okay. So each location has a set of clusters. So what would happen in the previous cases? What we have stored? See, it's for again remember radar. What have we stored? For each location we have actually stored a RSS value. Okay. For each location we have actually chosen our RSS value. Here we cannot choose a RSS value. We are choosing a set of clusters. Okay. So each location we are choosing a set of clusters, and when a test data comes, it checks that whether it matches with any of the clusters present. So what is happening? So see this thing over. So in the database you have for location 1, cluster 1, cluster 2, cluster 3, okay, cluster 4. For location 2 you have cluster 1, cluster 2, and it may be just cluster 3. In location 3 you have cluster 1, cluster 2, just cluster 2. In location 4 you have cluster 1, just one cluster perhaps. So this way you have kept all the location. Now new data comes. Okay, so new data comes and the new data would match best with any one of these clusters. So let me write it as 1 2 2 2 3 2 1 3 2 3 1 4 1 1 2 1 3 1 4 1. So this data similarity I mark with all CIIs. Okay, and it comes that it is best matching with C21. Okay, it is best matching. So we see the cross correlation. So that we have written that we see the cross correlation and it matches best with C21. And as soon as it matches best with C21, then we say that this point is at location L1. So this is the simple thing which happens. And so the location L1 is what we have seen, that since it changes very fast, location L1 is very precise. Unlike radar, unlike all other algorithms, here the location is very precise. And what is happening, what is the cost we are paying? Instead of keeping one value, we have to keep clusters of value. Okay, instead of keeping one value, we have to actually keep clusters of value. Okay, so once this is done, then the next question which would come, so fine, this is fine, we understand, but is it very stable? And what we have to see whether it is very stable or not with respect to environmental changes. So we have to see, because we are getting very precise thing. So at certain point we will want to see whether it is very stable with respect to environmental, whether it is stable with respect to environmental changes. So what type of environmental changes can happen? So what type of environmental changes can happen? So some interesting thing is, people will come, people will go. So people will go, people will come and move. Okay, this is, we have to consider, people will come and move. Okay, so what we have to see, the measure the cross correlation of CFR observed without and with changes. So if people is there, so let me think of an experiment. There is a Wi-Fi. Okay, there is a Wi-Fi, and you are this is the spot, and you are actually having a CFR, and the person is standing here. Okay, and person is standing at say x meters away. Okay, so what should be? So CFR with the person and CFR without the person. Okay, CFR with the person and CFR without the person. This is what we have to consider, that CFR with the person and and if I do CAB is equal to, so, and what I do, I just do a cross correlation. So I will take AIBI summation of EI square and summation of root over BI square. Okay, so I just take the cross correlation. So now let us see the result. Let us see the result. Okay, see this result, it is from on one AP1 and AP2. Okay, it is on AP1 and AP2. See this two results, AP1 and AP2. So what happens? See AP1. So AP1 is AP6230, and AP2 is AP5A10. Okay, so there are two access points. Okay, AP6230 and AP5A10. Okay, so there are two APs. Now x-axis is what? X-axis is CFR, and if we go on increasing, and y-axis is the CDF, and if we go on increase, see what is happening. What does this mean? This means the correlation, we have calculated the correlation with person without person, and the correlation is very high. So what is happening? The correlation less than say 0.99 is just 10%. The correlation less than 0.99 is 10%. So most of the time the correlation is 1. And what we have done, the person standing at 1 feet, 1 meter, 2 meter, 3 meter, 4 meter from the target. And see 1 feet, it is becoming a bit bad, but still it is very good for the others. While if you see the second result, in the second result this is not very good. Okay, in the second result we see in case of 1 feet, for 60% of, for less than, for 60% of the cases it is 0.75. The correlation is 0.75. Okay. So that is not very good news. So but now see, for AP1 good news, and for AP2 it is bad news, not so good news. So what will we do? We will basically combine AP1 and AP2. So we will take information from both and see whether it changes if the person is standing. If it does not change, at least for one, we are done. The second result is with door closed and door open. So you can have door closed and door open, and in this also we see that if the door is closed, only if the door is just 1 meter before you. So but in a museum you will be having a wall and the door would be much far away. So only if you are actually 1 meter from the door, there is some bad result, otherwise the result is very good. So the correlation is very high. Only see the red line. Red line is a little bad because the door is just 1 meter from the target. But if the I'm sorry, I'm sorry. So if it is much higher than 1 meter, then this problem is not there. Whereas if you see metal actually deflects a lot of signal. So if a metal is put, like if you have an original metal shelf which is now put, then it creates a lot of problem. Okay. So this is important. See, if I have a building, a metal shelf would not come every day. So if a metal shelf comes inside, then the readings changes. So once the room is actually reoriented or reorganized, then more results has to be taken. Okay. So this is about experimental or impact of environment. So now, so we have been talking a lot about that. We have been talking about a lot that how does we were telling that this is very sensitive to location. So as soon as the location changes like 12 centimeters, then everything changes. So now we see this. See, we see that if we are taking 2 points, okay, we are taking 2 points which are actually say x centimeters away. So x can be 0.5, 0.1, 1.5, 2 centimeters, 2.5 centimeters, 3 centimeters, 3.5 centimeters. See the picture. So we see that as soon as it goes more than 2 centimeters and becomes around 3 centimeters, the result becomes very bad. So you see in the 3 centimeter range, what is happening? The correlation around 0.5 is 0.5 or less is for 60% of the cases. So for 60% of the cases, what we are seeing that the correlation between CFRs of 0.1 and 0.2 is, so CFR, so if I have positions, I have this is say 3 centimeter and this is point A and point B, and I am calculating CFR A minus CFR B, or correlation between CFR B, the correlation that is less than 0.5 for 60% of the case, which is very bad, although they are just 3 centimeters apart. So what we understand, 2 centimeter is the best value. So around 2 centimeters, if we have distance of 2 centimeters, then the data would be same, but if we go beyond 2 centimeter, the data would be very different. So what was happening is, again, can CFRs for one location be same as CFR of other location? So this also we can see that it can be same for with respect to one AP, but as soon as we take multiple APs, this would never be same. So all CFRs of all locations would be very unique. So CFRs of all locations would be very, very unique. So that is also needed. So we put, so it is not only CFRs of closing locations should be different, but CFRs of any two locations taken apart should be very, very different. This graph actually says this. So see this graph, x-axis is showing that how much is similarity when between two locations. So similarity between two locations would be always positive. Okay, should be always positive, and that is what is showing that if it is negative, it is the probability is very low. Okay, so now what is happening? The idea is fine. So, but who wants 2 centimeters? Think carefully. See, now there are issues. Issues are that who would want a 2 centimeter plus 2 centimeter localization? No one wants. Even if I stand, I am actually taking maybe 1 feet by 1 feet. Okay. If I am even standing, I am taking 1 feet by 1 feet. So what happens? So what happens is that don't localize for a location, but localize for a spot. And what is a spot? A spot is 1 meter cross 1 meter, which consists of say n 2 centimeter cross 2 centimeter locations. Okay. So don't localize for a location, but localize for a spot. Okay. Is that clear? So when we localize for a spot, then what happens? I think we have very less time. So what we are exactly doing is, we are doing this very simple thing. We are doing this very simple thing that you have localized spots. So let me go back to this picture and tell you that we have localization for a spot. So I will leave you the slide so you can go through the slides and see in the details. So now you take spot 1, spot 2, spot 3. So location 1, location 2, location 3. Okay. So now you see that in how many locations it is matching. So what is happening? First use radar. What would give you radar? Radar would immediately localize to certain area. Okay, because radar has like 2 meters radius. So you have this. So you will be localized into this using radar. So this has various spots. So spot 1, spot 2, spot 3 and spot 4. So each spot has various locations. Okay, and what you are getting, CFR is in for each location. So now you get CFR for 3 locations. So CFR for 3 locations. Okay, you get CFR for 3 locations. So now check a majority that this CFR for 3 locations which you have taken, this matches best here, best here, best here or best here. Wherever it matches best, that is your location, that is your spot. So what is happening? So all the other techniques like other localization techniques can localize you in a reasonable area within 2 meters 3 meters cross 3 meters, but you want 1 meter cross 1 meter. Fine. So first you are localized into 2 meters cross 3 meters, which will have say 5 1 meter cross 1 meter. Now your point is I have to be localized into this exact 1 meter cross 1 meter. And what have you collected? You have basically collected various CFRs. So say you have collected 5 CFRs. So these 5 CFRs, so for each of these locations there are many spots. Okay, so there are many spots. So now I put these 5 CFRs into each and see that in which spots which it matches best in which locations. What does it matches best in which locations means that each spot has, so there is spot, so don't mix it up, spot is the bigger one and then it is location. So I have 5 CFRs and this would match with say L1, L2, L3, L4, L5. Okay. So now L1 is in spot 1, L2 is in spot 2, L3 is in spot 3, L4 is in spot 3 and L5 is in spot 3. So I see that out of this 5 matching, 3 are in spot 3. So I am in spot 3. Simple, I have a majority and I am in spot 3. So this is how spot localization happens. So then this is actually very accurate, that you have a 1 meter cross 1 meter localization. So this is the experiment they did. They did it on Duke Museum. So it was work done in Duke. So they did it on Duke Museum. Then they did it on Duke Museum. Then they did it on the EC building of Duke, and they did it in the cafe. So 3 places they have done this, and they have Roomba. So see, the point is very simple. Point is that even calculating, even getting the word driving, even doing the word driving is difficult. Why doing the word driving? Because you have to have 1 centimeter, 2 centimeter to cross 2 centimeter word driving, and 2 centimeter cross 2 centimeter. You telling a person, in the previous case was what was happening in radar, person was moving with his, the person was moving with his mobile phone. Okay. In the previous case, the person was moving with his mobile phone or laptop, etc. But here, even if a person moves like this a bit his hand, then it will cross 2 centimeter cross 2 centimeter. So word driving would has to be done with a robot. Okay. So do it as word driving with a robot. And then another point which has to be remembered, this 2 centimeter to cross 2 centimeter, you cannot get word driving for each and every location. So you have to keep some location. So for one spot, you may keep 50 locations. Okay. So this is what they get. They get 90% accuracy. They get 90% accuracy. Let's see, this is the accuracy. They get 90% accuracy. Wi-Fi RSSI performs poorly. Wi-Fi RSSI, all these other things doesn't perform well. So they get 90% accuracy. And as soon as they know the but they have to do, as I have said, that macro locationing, that first radar or any location algorithm has to give them the macro locations from the big to small, and once they are in the small, they know that there are 14 spots, 6 spots, 8 spots, 9 spots, and accordingly they can actually do the localization. Okay. So then what is happening again so there is a lot of work they have done, that they have taken test packets, they have impacted number of APs, what is the impact of word driving. So if you go through this paper, this is very detailed paper. Just if you have time, go through this paper, very detailed paper, which actually sees all the parameters in very great detail. But the bottom line is, again, if you are standing in front of Mona Lisa with 90% accuracy, it will give you the information of Mona Lisa. Okay, so I have to wrap up. So what we have, thank you for attending. I think although we have not interacted much, I have enjoyed taking this class, and what we have taught, the first thing, just to, so we have done the outdoor localization using GPS, then we did the indoor localization using radar, then we did the reverse localization about cell towers, and again we came back to precise indoor localization. So now I think I have given you a bit of idea both about outdoor localization and indoor localization. I guess many of you are teachers, so you will go back and take this rich thing about smartphone computing, about localization, how location is identified in smartphone computing, and teach your students later. Thank you.